Hello students, in the last video we discussed about the inductive effect, the applications and formulas. So based on the all conditions, now we will discuss about the stability of the carbocations according to the inductive effect only. Then in this, the first case CH3 CH2 plus carbocation. Next, second one CH3 C plus CH3 bond CH3. Next, third one CH3 CH bond CH3 the plus. Fourth one CH3 plus. So these are the carbocations. So how to identify the stability of the carbocations in the given four compounds? Now, so this is the main carbocation. We have to identify the stability of this carbocation. Here this one is the carbocation. Here this is the carbocation. This one. Now, first, how to identify the stability for this given compounds? Now, this complete CH3 group, it is acts as a plus I group, inductive plus I. Now, that means it totally release the electrons. This one also plus I group, plus I. This one also plus I. Totally, these three groups here donated the electrons towards carbocation. In this case, 1, 2, this group also plus side, this one also plus side group. But if you observe in this case, hydrogen atoms will be present. Hydrogens are neutral atoms. Hydrogen is neutral. Already we discussed this one. It is neutral. Now, according to the inductive conditions, plus side group increases the stability of the carbocation. Already we discussed in the last video. Plus side directly proportional to stability of carbocation. Carbocation. So in this case, now which one is more effectively release electrons? Here, three inductive groups increases. Here, 2 plus I groups increases the density. Here 2. Here 0 plus I groups. So there is no change in the stability. Here coming to this one, 1 plus I group. So which one more effectively release electrons? Second one. Now the stability order for this, 2 is greater than 3 is greater than 1 is greater than 4. So this is the stability order for the given carbocations. So this stability order we can identify according to the inductive effect. According to the inductive effect. This is the one example. Then next, another example. So how to identify if any other group is given. So that time we can identify easily the carbocation stabilities also. The next another one is second example. CH3 CH2 plus, this is the compound one. Next second compound C2H5 CH2 plus. So in these two, which one is the more stable carbocation? Now, in this given condition, first identify how many groups releasing the electrons towards carbocation. Here only one CH3 group. One. This one is the plus I group. Now here also one group only release the electrons towards carbocation. But now this group is also acts as a plus I. According to the plus I order, already we discussed that order, C2H5 more effectively release. That means it is a displacement effect. Displacement of electrons towards carbocation. Here only CH3 group, here C2H5. C2H5 always more effectively release electrons than CH3 group. Now, second one is more stable than the first one. So this is the stability of the carbocation. The second example you can identify like this. This is the one case. Next, third case. We will discuss in this video mostly the most of the examples. Next one, CH3, CH2 plus, this is the one more carbocation. Next, second one is CH2, CH2 plus, here fluorine. Next, third one, CH2, CH2 plus, here fluorine. Fourth case, CH2, bromine or iodine, whatever it is, take bromine. Here CH2 plus. Now, identifying this, the carbocation stability. So generally in the before cases, all are the plus I groups. Now in this condition, here CH3 group is attached to the CH2 plus. So this group alone, it acts as a plus side. It releases the electrons. Here it is releasing the electrons. Then coming to the second condition, when fluorine atom is attached to the carbon, instead of releasing, now this one withdraws electrons from the carbocation. That means it decreases the stability. Fluorine is decreases the stability. Why? Because fluorine is belongs to minus I group. Now here also again one more fluorine atom. It is also acts as a minus I. Now this one decreases the density. Instead of releasing, it withdraws electrons from the carbocation. Same here also same situation. Bromine is belongs to minus I group. Here also it is decreases the stability like this. Now, just now we discussed this formula. Plus I release the, that means increases the stability. Minus I group, it is inversely relation with the stability. So it is inverse relation with the stability. Minus I. Here only I will write. Minus I group, it is inverse relation with the stability of carbocation. So because of this reason, second, third, fourth, these groups are least stable than the first one. So which one more stable now? First compound is always more stable. Why? Because releasing group is present. Next in these three, 2, 3, 4, second one is a more effectively withdraws electrons. The minus I effect is more. If more effectively withdraws means it is the least stable. Now, which one is after the first compound more stable? Fourth compound. Now, 4, next 3, 2. This is the order for the stability of the compounds. Stability of the compounds. Okay, so we can identify the stability of the carbocations by using this formulas and groups plus and minus I effect conditions. Next, we will discuss few more examples also based on that all conditions. Next, another one is another example. So you have to memorize the order plus I and minus I order. If you know that order, you can easily identify the plus and minus I groups. Stability also we can say easily. Now, first one CH2 plus, here one NO2 group is attached. Next, second one CH2 CH2 plus. Next, third case CH2 NH3, here plus, here also CH2 plus. Next, fourth case, CH2 plus 1 OH group. Next, fifth one, CH3 CH2 plus. So these are the 5 compounds. So write the stability order for the following given compounds. So how to identify the stability of the given molecules? Then first here it is CH2 plus is common. We are discussing about this carbocation on stability. So here first identify here one group is attached to the same compound. It is act as a minus I group. Next second compound cyanide group also minus I. Next NH3 plus this one also minus I group. Next OH group minus I. But the CH3 group already acts as a plus I. So plus I groups always release the electrons. That means stability increases. So which one is more stable in all cases? So fifth one is always more stable. We can write, we can say directly, fifth one is always more stable than the first four. Then in these given 4 compounds, which one effectively withdraws electrons? Here all are withdraws electrons from the carbocation. Okay, like this it withdraws electrons only. Okay, all are withdraws electrons from the carbocation. So after withdraws electrons, which one? According to that order, already we discussed the order. So according to that, NH3 plus is effectively withdraws electrons. If it is effectively withdraws electrons, means the stability, positive character increases more. The density, electron density decreases more. If electron density decreases, means the neutralization process is very, very less stable. So that's why here, third one is the least stable than all. Now identify the remaining all cases. 4. According to that order, OH less effectively withdraws. It is a next stable compound. So after that, cyanide, nitro group and NH3, cyano group only less effectively withdraws the electrons. Next, second. After that, NO2 group 1. Least stable is the third one. So this is the stability order of given organic compounds. This is the stability order of given carbocations. So this is the one kind of identification based on the plus I and minus I groups. Next, another example. Next example. CH3, CH2 plus. This is the one compound. Next, second one. CH2 double bond CH plus. Third one. CH triple bond C plus. So these are the 3 compounds given. So in these 3, which one is more stable? How to identify that? Then next case. Here, first identify the carbon, type of carbon which is attached to the carbocation. It is sp3 hybridized carbon atom. sp3 hybridized carbon atom. Now the next, the second carbocation, it is sp2 hybridized. The third case it is sp hybridized carbon atom. In the before cases, the carbocation chain same only, but in this case, this one has double bond, triple bond, and single bond. Before cases all are the single bond cases. In this sp3, sp2, sp, the identify the hybridization in this first one sp3, second sp2, third one sp. Now it depends on the percentage of S character. So percentage of S character in this, percentage of S equal to 50 percentage. Now in the second case, percentage of S character, so totally 3. So 1 by 3. 1 by 3 means nearly it is 33.33 percentage. Next, The first case it is 1 by 4 case 25%. So if the percentage of S character increases, percentage of S character increases, electronegativity increases more. Electronegativity increases. If electronegativity increases, what happens? The electron withdrawing nature increases. If the electron withdrawing nature increases means the stability of this carbocation effectively decrease. So based on that, which one is more stable now? First compound. This group effectively release electrons. This one more stable compound. After that, second one. Next is third. So it depends on the stability of the carbocation depends on percentage of S character. Okay, percentage of S character. It is very, very important. So these are the few important questions in stability of the carbocations. So next, another one is stability of carbanions. Stability of carbanions. Stability of the carbanions. So what are the formulas already I give? Suppose if a plus I group is attached to the carbanion, it is inversely relation to the stability of the carbanion. If a minus I group attached to that carbanion containing chain, it is directly relation with the carbanion stability. So remember these two. Now we can easily identify the stability of the carbanion. So negative charge on the carbon. Same like one more example we will discuss now. One CH3, CH2 minus negative charge, carbanion. Next, CH3, CH bond, CH3, here negative charge. Third case, CH3, C bond, CH3 bond, CH3. So tertiary butyl carbanion, secondary butyl carbanion, secondary propyl carbanion, it is primary ethyl carbanion. Ethyl carbanion, propyl isopropyl carbanion, tertiary butyl carbanion. Next, fourth case is CH3 minus, simple carbanion. In these four cases, so what is the stability order? Then first in this, as per the given formula conditions. Now, plus I groups, all are the plus I groups. It is plus I, plus I, plus I, plus I, plus I. So in these three cases, only plus I groups attached here. If a plus I group is attached, what about the stability? Decreases. If a minus I attach to that stability increases. So remember these two based on these three compounds, first three carbanion stability less. Which one is more stable now compared to these three? Fourth one is more stable. Okay. Fourth one is more stable than in these three cases. One releasing group, two releasing groups, three releasing groups. So one releasing group containing carbanion is more stable. So 4, 1, next 2, next is the 3. So this is the stability order of carbanions. It is the reverse of the carbocations. So we can say easily the carbanions stability like this. In the before case also we discussed the same like S character, percentage of S character like that. Here it is reverse only. If tertiary conditions, what happens here? Oh, sorry, here percentage of S character means sp3, sp2, sp conditions. Now, if percentage of S character increases, sp related carbanion stability is very high. So CH triple bond C minus is greater than CH2 double bond CH minus is greater than CH3 CH2 minus. So this is the another case we can say directly. Just now only we discussed that related same compound here. This one, this case. Same here, it is reverse. Percentage of S character. In this case, it is directly relation with electronegativity means carbocation stability decreased. But in this case, carbon ion stability increased. It is reverse. Okay. So it is neutralization more in this case. It is a sp hybridized carbon. Here it is sp2. This one is sp3. So this one is the carbon ion stability. We can say that directly. Now, carbon free radicals means already we discussed. It is also same as like carbocations. Now, stability of carbon free radicals. Stability of carbon free radicals. Same as like carbocations. Carbocations. Just one example only we will discuss. So in this case, the formulas already we discussed here. Same like plus I is directly relation with the carbon free radical. Minus I is inverse relation with the carbon free radical. Here this one stability decreases. Here this one stability increases. So that is the difference in between the plus I minus I group conditions. According to these two, just one example only we will discuss. Just one example. Somewhat different one example only we will discuss in this. So first one, CH3, CH2, free radical. Next, second one, CH2, NO2, CH2 free radical. Third one, CH2, here, CN, CH2 free radical. Fourth one, CH2, O minus, CH2 free radical. So in these four cases, so which one is more stable? Here that one release the electrons towards CH2 free radical. This group already acts as a plus side. So plus side group always increases the stability of the carbon free radical. Next, but in this case, instead of here releasing this group minus I group only, it pulls the electrons from the carbon free radical. Now, what happens here? The carbon free radical stability decreases. Here also cyanide group, it acts as a minus I. Again, it is withdraws electrons from the carbon free radical. Next, here O minus group. This O minus group acts as a plus sign. It releases electrons towards a carbon free radical. Then which one is more stable in this? Two minus I groups, two plus I groups. Plus I groups always increases the stability. Minus I groups decreases the stability. So plus I groups in this O minus is effectively withdraws electrons already order. So 4 is always more stable than the first one. We can say that directly by using these two. Next, in these two, NO2 and cyanide, NO2 group effectively withdraws electrons. So second one is least stable than the third. Least stable. So 3 is greater than the second one. Now this is the stability of the free radicals. So it is also same as like carbocation conditions. So by using this, we can easily identify the stability of the carbocations and carbanions and free radicals, carbon free radicals. Next, we will discuss another one in this alkyl halide. Another application that is reactivity of the alkyl halides. Reactivity of alkyl halides. Now, the general formula of alkyl halide is RX. This is the general formula. So in this general formula of alkyl halides, it exists in the nature primary alkyl halide, secondary alkyl halide, tertiary alkyl halides. Primary, secondary, tertiary alkyl halide. That means if only one R group is attached to the halogen, it is primary alkyl halide. If R, CH, or X given means this one is secondary. That means X attached to the secondary carbon. This is the secondary carbon. Next, another one is R, C, R, R, X. This group is tertiary alkyl halide. So these are the alkyl halides representations. So totally here three alkyl halides only given. In this next we will discuss that reactivity. Now one important point here. So the reactivity of alkyl halide, reactivity of alkyl halides depends on stability of carbocation. Stability of carbocation. So how it is depends on the stability of the carbocation. We will discuss now about the alkyl halide reactivity. So in this alkyl halide reactivity, so generally we will discuss R CH2 X R CH R X R C R X. It is a primary alkyl halide. This one secondary. It is tertiary. So in these three given cases, first remove X minus from this given condition like this. Here also remove X minus. Break the carbon halogen bond from this alkyl halides. Now remove X minus. Here also see X minus. Then after the removal of that halogen with the bonded electrons, then you will get R CH2 plus. Here we will get R CH R plus R R plus. It is a primary carbocation after removal of halogen. This one is secondary carbocation. It is tertiary carbocation. So this reactivity depends on the stability of the carbocations. Generally, we know that carbocations which one more stable. Just now only we discussed. Tertiary is always more stable. So why? Because how many releasing groups are present here? Plus I, plus I, plus I. Here 3, here 1, 2 releasing groups. Here only 1 releasing group. So totally in these given conditions, 3 releasing groups here more stable. After that, 2 is more stable. Next one is the less stable. The stability of the carbocations increases here more means it is more stable carbocation formed means this alkyl halide is more reactive. So the reactivity order, reactivity is tertiary is greater than, secondary is greater than primary. Based on the condition, stability of alkyl halides. So now I'm explaining here stability of only alkyl halide only. That is primary, secondary, tertiary. So these two cases only for the alkyl halide. Next, another one, reactivity of a carbocation. Which one more reactive now? Reverse. It is more stable means this one is more reactive. Primary, secondary, tertiary. So stability order, stability of this one, tertiary, secondary, primary. So on the basis of these conditions, one important formula, reactivity is inversely relation with the stability. Inversely relation with the stability. So this formula is very, very important. So don't compare here these two. I'm not writing here reactivity stability for both. One only. It is for only carbocation. It is only for alkyl halide. Okay. So next other examples and other applications we will discuss in the next video. Thank you.